Allow me to thank the organizers for this kind invitation and for the opportunity to share my research with you. Just a quick disclosure, I'm listed as an inventor and on the FRAP test. I'm also a consultant with Idiot Neurosciences and Cox Biosciences. The latter is involved in developing a new generation of folinic acid treatment, and I'm going to discuss off-label use of folinic acid. So for the audience who may not be familiar with folate, I just want to introduce you to some terminology here. Folic acid is steroid glutamic acid, it's vitamin B9, and folic acid is a pharmaceutical preparation. It does not exist in your body. Methylfolate is 5-methyl tetrahydrofolate. It's a reduced form of folate. It is the predominant circulating form of folate, and it is also a predominant intracellular form of folate. Folinic acid is again a reduced form of folate, N5-formyl tetrahydrofolate. This is a form that has been recently tried in clinical trials for the treatment of autism. So I'm going to also use the term folate to represent intracellular metabolically active forms of folate. They represent the whole pool of folate within the cell. I'm also going to describe an autoimmune disorder and two types of antibodies. When I say blocking antibody, this could be an IgG or an IgM antibody, and it binds to the active site or where folate binds. I'm also going to describe to you a binding antibody that does not prevent folate binding, yet it binds to its antigen, which is the folate receptor, and likely triggers an immune reaction and inflammation. So both antibodies, whether they are blocking or binding, they are immunogenic, they create inflammation locally and destroy the antigen, but the blocking antibody, in addition, can functionally block folate transport into the cell. So folic acid story is very interesting. I see a lot of fellow Indian compadres here, and the whole story goes back to what is now known as Mumbai, India, where a young British physician, Lucy Wills, in 1931, described pernicious anemia of pregnancy and tropical anemia. These are the women who used to come to her clinic at the Haskell Institute, which still exists as a premier immunology institute, where I got my first training in immunology. So Lucy Wills found that these women would come to the clinic with anemia, they had pregnancy-related complications, so finally she identified it's a new micronutrient which was present in yeast, and ultimately in 1940 it led to the purification and identification of folic acid at UC Davis from a truckload of spinach, and hence the name folic acid. So most of you here, well, there are new faces, but those who were yesterday and the day before know these pathways, so I'm going to quickly, briefly describe them for you. So here we have the methylation cycle in blue, where B12 and folate interact. We have then the glutathione cycle. Glutathione, as you know, is an intracellular compound that stabilizes the redox state and makes a lot of enzymes work efficiently. Then we have the folate cycle in green, where you basically show all of the folate-dependent pathways. Most important of all is they are involved in synthesizing the basic nucleotides, purines and pyrimidines that make up the DNA and RNA. And then in the brain, it acts for the production of tetrahydrobiopterin, which is the cofactor for synthesis of neurotransmitters from amino acids. And this is why folate deficiency has such a profound effect on the body. So I'm also going to describe you how folate is transported into the body if you take it orally. And the terminology I'll use is the proton-coupled folate transporter, which transports all forms of folate that are in your diet, or if you're taking a vitamin pill, irrespective of what form it is. Then there is the reduced folate carrier. It does not transport folic acid, the pharmaceutical preparation. And then we have the folate receptor alpha, which transports folic acid and 5-methyl, which is the predominantly circulating form of folate, but does not transport folinic acid, which is the treatment for cerebral folate deficiency in autism. So absorption of folate, again, considering the time limit I have, I'll go very briefly. This is showing in the gut, orally, most of the folate is absorbed in about upper one-third of your intestine, and that happens via the proton-coupled folate transporter. The folate that is absorbed is primarily converted into a form known as methylfolate. So even if you give folic acid, it is rapidly converted into methylfolate because there is a lot of dihydrofolate reductase and MTHFR activity within the gut. So it ends up as methylfolate in the circulation. Then it goes through the first pass in the liver, where it can go into cells and be converted to further reduced forms. And then it is distributed all over the body to various tissues, including the brain. Now, in the brain, there is a very special system here. There is a blood-brain barrier. So things that the brain has to take up have to cross the blood-brain barrier. And here is a human choroid plexus, which separates the spinal space, fluid space from circulation, showing you on the left top H&E staining of the choroid plexus. The red-looking substances there are RBCs within the microcapillaries. Then the immunostaining for the various folate transporters is showing you reduced folate carrier, the folate receptor alpha that exists shown on the bottom left corner, and folate receptor beta, which I will not touch upon today. And similarly, others have found high expression of the folate receptor alpha on the choroid plexus, and this then acts as a transporter of folate from the circulation into the brain. Shown here diagrammatically how this process occurs is the brain showing you in the middle the cerebrospinal fluid space, and the lining which is the choroid plexus epithelium. So on the right-hand side, there's an enlargement of the diagram showing you that the folate receptor on the surface, expressed in red, is internalized when folate binds to it, and then it forms a microvesicle known as exosome. These are very specialized vesicles that trap ligands and receptors within them, and that vesicular transport then goes into the cerebrospinal fluid, and from then on, that is taken up by the ependymal cells of the brain periphery and transported into neurons and other cells within the brain. Now, why is folate important for brain structure and function? Here shown in the diagram is rat brain from left to right from day 12 to day 18, and you can see how much proliferation and replication is taking place. The size tells you that tremendous growth of the brain occurring during this phase. This phase represents, in terms of human brain development, day 34 to day 144 of fetal development. And for this, folate is very essential because cell replication involves DNA and RNA synthesis and active metabolic processes. So what happens in folate deficiency is you have metabolic effects, you have effects on cell replication, you have then, because folate is also involved in methylation, you have epigenetic effects, you have decreased neurotransmitters formation, you also have homocysteine, which is a metabolic product when folate pathways don't operate, and homocysteine then buildup can interact with various proteins in the brain and inactivate them. So this homocystylation is an active process which inactivates brain proteins. Again, all of these have an effect. Now this is all during the top panel showing during fetal life, but even after birth, shown on the bottom right-hand side, you can see this is the rat brain shown size-wise from day 10 to day 23. It almost doubles. This is akin to looking at a newborn brain during the first year of life. There is a tremendous growth there, and there is lot of changes occurring, and these changes are mainly in terms of connectivity and loss of connectivity, and it's like a repair process which establishes the ultimate connectivities that are needed for the brain to operate. And anything happens to this process can result in neurologic disease. Now, as you know, in the US, grain is supplemented with folic acid, and that has now reduced the prevalence of neurotube defect pregnancy. And as you can see from this graph, all the countries that have grain supplementation, it has reduced to some extent, but it has not eliminated neurotube defect pregnancy. So the reason for that is there are other causes, okay? And we will get to that. So we wanted to study this in a rat model, making the rats folate deficient. And then we wanted to see what effect this would have on fetal development. Unfortunately, as we were looking at this model, we realized that if you make the rats folate deficient, they don't get pregnant. Okay, that created a huge problem. And we said, okay, how can we study fetal folate deficiency in rats and not affect their pregnancy? So we said, well, could an antibody to the folate receptor, which is involved in transporting folate from the mother to the fetus, could that be used to block folate transport from the mother to the fetus and create this artificial folate deficiency in the fetus? And so we went ahead and we purified the folate receptor from the rat, and we made a recombinant protein, we purified the recombinant protein, we made an antibody to this, and we gave it to pregnant rats. And here is the effect of that. So when we gave the antibody at higher doses, we noticed that rats which we knew were pregnant on gestation day 8, they never delivered. What happened here? What happened to the embryos? So we opened the rat on GD8, counted the embryos and gave the antibody, and realized that the antibody was totally destroying all the embryos. So we then titrated the dose down because we wanted life ups. We wanted to know what effect this would have on brain function. So when we titrated the antibody titer down, we could now see this is a gestation day 15 embryo, and the top two panels are where antibody exposure took place. And if you look at the top part where you see open space, that is the area where the neurotube formation took place, and you can see that's very large, it's disorganized, and so the neurotube formation and the ventricle formation is not adequate or proper. If you look at the bottom panel on the left, you can see where we took the antiserum by affinity chromatography, we pulled out the antibody that specifically reacts with the antigen. And the rest of the IgG, we gave it to the pregnant rat, and you can see this time the complete neurotube development took place and the closure took place. That means what we prove from this is the antibody is very specific for the folate receptor alpha. It's not a non-specific antibody effect. Okay? And if we didn't do that, but if we simply gave a pharmacological dose of folinic acid at the time of antibody exposure, then again we prevented neurotube defects. And we tried to understand the underlying mechanism. We gave the antibody, and then histochemically we looked at the antibody distribution within the embryo. So on the right-hand panel, you can see that brown staining is all antibody. You can see that the tremendous load of antibody within the placenta, and a small amount also does go to the embryo. And you can see on the left-hand side, it's a diagrammatic representation of quantity of antibody going to the uterus, to the placenta, and a tiny amount going to the embryo. Now in the and you can see even in lower panel, we're showing antibody collection in the choroid plexus and in the snout of the embryo as it's developing. Now if you go to the bottom left-hand diagrammatic representation, we now looked at what happens to folic acid distribution if the antibody is there. So we give radioactive folic acid to see how it distributes in the presence of antibody. And you can see in the uterus there is the panel, the very light gray area bar is normal without antibody, and you can see that a lot of the folate goes to the placenta and ultimately goes to the embryo. Okay? However, if the antibody is there, where you can see the lighter and the black bar, you can see that there's a significant decrease of folate going to the embryo. So the antibody is blocking folate transport across the placenta into the fetus. So what is the relevance of all of this? We have now shown that in a rat model, we can show that exposure to an antibody causes neural tube defects. We said this won't be that relevant if we can't show that antibody exists in women who have a history of neural tube defect pregnancy. Then it becomes very relevant. So we looked at a small number of women who already had a history of neural tube defects going back a few years, and we looked for the folate receptor antibody. Now this is human blood, so it really is an autoantibody because it reacts with their own folate receptor. And you can see from the bar graph here that about 70% of the women who had a history of neural tube defect pregnancy had the folate receptor antibody. Now this explained a very puzzling observation that has been observed in the neural tube defect research community. They knew that supplementing brain with folate reduced the incidence of neural tube defect pregnancy. That was done because if physicians gave folic acid prenatally during pregnancy, it really didn't help because the neural tube closure occurs in the human on day 23. And by the time they go and see a doctor that they are pregnant, it's too late. So this is why it was introduced into the grain, yet, physicians will recommend folic acid supplementation throughout pregnancy. So now we had a link that an autoantibody to the folate receptor can basically create folate deficiency in the fetus. And we knew this because mothers who have a neural tube defect pregnancy are not folate deficient by any criteria. So biochemically they're not folate deficient. Yet the fetus develops neural tube defect. And it is the presence of the autoantibody explaining that this is exactly what could happen. If the woman is positive for the antibody, the fetus will be affected. So following this, we extended our observation to a group of patients in Europe who had a condition known as cerebral folate deficiency syndrome. The neurologic presentation overlaps quite a bit with low-functioning autism. They develop severe neurologic disease, and typically these kids are born quite normal-looking, and the disease sort of presents itself when they switch from mother's milk to formula. Okay? And during this time, their cerebral folate levels go way down, and the physician who was doing these studies didn't know what was causing it. So he looked at all of the genes in the pathways, he looked at potential neurologic, other genetic disorders, and couldn't find anything wrong. So when we published our first paper in New England Journal of Medicine with neural tube defect pregnancy and the autoantibodies, he contacted us and said, I have these patients, they have low CSF folate, and I don't know why, but yet they respond to high-dose folinic acid. So when we looked at these patients, seen at the bottom there, the bar, 89% of these kids were positive for the folate receptor autoantibody. So this provided an explanation why they have low CSF folate, because the antibody blocks folate transport across the choroid plexus into the brain. Okay? And there's a correlation with the higher the titer, the lower the CSF folate levels shown on the right-hand side. So when we published this paper in 2005 in New England Journal of Medicine, Bob Schwartz, who was the deputy editor of New England Journal, wrote a very provocative editorial, partly based on a discussion that this switch from mother's milk to bovine milk triggers increase in antibody titer. And basically he called it autoimmune folate deficiency and rise and fall of horror autotoxicus. Those who know the history of medicine, the term horror autotoxicus was coined by Paul Ehrlich in the 1900s because when explaining how an antigen-antibody reaction occurs, he said, he defined the self from non-self theory, and he said, you can't recognize your own antigen because that would be horrible. That would be horror autotoxicus. Yet, so later on, Landsteiner described antibodies to the self proteins. What he said was, no, we can form antibodies to our own proteins and to some extent. Some of them are harmless, some of them could be toxic. So what he did here is diagrammically show that very nicely that yes, milk intake, which contains a lot of folate receptor, can trigger autoimmune exposure to the milk antigen to the lymphoid system in the gut, and this could then increase the antibody production. So we actually took some patients who were positive for the antibody, put them on a milk-free diet, and lo and behold, their antibody titers dropped. When they went back on milk, their antibody titers went way up. So again, establishing that connection. And the reason for that, we found that here is proteins, folate receptor alpha from different sources, and you can see that we are showing comparative reactivity. The antibody reacts highly with bovine milk folate receptor, and to a lesser extent with goat milk. So there is that reaction between the autoantibody and milk protein. Here we looked at human, bovine, and camel milk because a lot of people in the autism circle think that the camel milk is harmless and they've been giving their kids camel milk. In fact, if you look at the right-hand side, camel milk is highly reactive with the autoantibody, and it really raises the titers. So it's a bad thing to give camel milk to these kids. Okay, so now we have shown that autoantibody is associated with neurotube defect pregnancy, subfertility, preterm birth, low-functioning autism, Rett syndrome, and autism spectrum disorder. Maybe we could look at other conditions such as ADHD, depression, and dementia, and maybe we'll find a link there. So the one criticism of our studies has been that all this is an association. So the autoimmune disorder is associated with all these conditions. So we wanted to prove that it is more than an association. So those who know Koch's hypothesis, which was advanced in between 1800 to 1900, was that if you see a bacterium that causes disease, to prove that the bacterium causes a disease, you have to take the tissue from an affected animal, isolate the bacterium, and then inject it into a healthy animal and show that that bacterium causes a disease. That was Koch's hypothesis. So we wanted to show something similar, and what we did was we basically made an antibody to the rat folate receptor and wanted to show that we can create a rat model of folate deficiency. Give me a few minutes. And I'm going to touch upon number 3, which is folate receptor antibody exposure. Okay? Why did we pick the rat? Rats are very intelligent. You use them for behavioral studies. Here is the New York subway. The rat has now started a pizza delivery system. Okay? So they learn, they're very smart, and so they're ideal for behavioral studies. And I'm not going to go through all the behavioral studies, but I'm going to show you one. Here is the arena where the rat learns to avoid a shock zone. So it's a process known as active avoidance, and what the rat is doing is he's learned this invisible shock zone is there, and he can, by running around away from that spot, he can avoid the shock. He's looking outside the arena because cues inside the arenas don't help in the rotating arena. Using these techniques, we can measure basically learning, memory, and cognition. And here's the summary of those results. You can see rats exposed to during pregnancy, gestation day 8.8, when you give the mother antibody, the pups born have severe behavioral deficits. They have learning deficits, they have memory deficits, they have cognition deficits, they have set shifting deficits, which is basically teaching them a task and asking them to learn a new task, and they can't do it. Okay, so these are very severe learning deficits. Now, I know I'm running out of time. Give me 2 more minutes. I want to just introduce this very interesting. So the rats develop behavioral deficit. The question we asked was, could these deficits be transmitted to subsequent generations? And what could be the potential mechanism? So here you're looking at basically generation 1, 2, and 3, but 3 wasn't completed. This is all very new data, and you can see that behavioral deficits are transmitted across generations. So the question now to ask is why, how could this happen? So that means there are genomic and epigenomic changes occurring from that first exposure. Second would be a germline transmission, but if the deficits go to 3rd and 4th generation, it is truly epigenomic. And we want to look at this, we want to find out what are the epigenomic changes responsible for this transgeneral transmission, and whether it's coming from the maternal side or paternal side. This is a project that's going to need a lot of money, so if people here have deep pockets, please come up with the money. Okay, I'm going to skip this because I just want to show you something very relevant to some people here. So we wanted to ask the question, which is the best form of folate for treatment of autism or cerebral folate deficiency? We looked at folic acid, we looked at 5-methyl, we looked at folinic acid, which is already used in clinical trial, and we also used the newest available form of folate known as levoleucovorin. So DL-folinic acid is mirror image. One half is not active, the other half is active, while L-folinic acid is 100% active. And we did this in rat model, and you can see here we looked at from 30 minutes to 4 hours, looking in the blood, absorption of orally administered folate, and as you can see, folic acid, 5-methyl, leucovorin or fusilin, which is levoleucovorin, all are taken up, typically reaching a peak absorption around 1 hour, and then kind of tapering off. And now if you look at how much of that is converted into methylfolate, as I indicated to you, most of that is converted into methylfolate, and tetrahydrofolate is another intracellular forming, and you can see that a lot of this is converted, but you can see with the last panel here, levoleucovorin, you can see a lot more conversion, and methylfolate is transported unconverted. That's why you're seeing the higher bars there. Folic acid, on the other hand, you can see some of it is converted, some of it is not, and if you can look at the unconverted form here, there's a lot of folic acid transported across the gut into circulation unconverted. Methylfolate goes in as is, but DL-folinic acid and levofolin, there is some original material still left after 4 hours, during those 4-hour period in circulation. The rest is converted into methylfolate. Okay. We're going to skip this, we're going to skip this, we're going to skip this because I think I've been warned. Okay, so just to summarize, at pharmacologic doses, orally administered folates peak in the blood between 30 and 60 minutes as unconverted and converted to methylfolate. While all forms are similarly distributed to the liver and kidneys, distribution to the brain is better with the reduced folates. Levofolinate appears as the preferred form to treat fetal and cerebral folate deficiency and has the advantage of being available for metabolic reactions without needing MTHFR, MS, and DHFR in the first round of utilization. So it becomes readily available for folate-dependent reactions. So this is a future direction. What can we do? Where can we go? Can we extend these observations in the animal models to the human disorder? Can we treat mothers and fathers with folinic acid to prevent neural tube defect pregnancy, to reduce risk of autism in the offspring? Can we treat infants with folinic acid to prevent development of autism? These are the questions we will address going forward. And these are all of the collaborators, funding, and so forth. Richard Fry, you guys know, Vincent Raymaker, who provided the first cohort of cerebral folate deficiency syndrome, Jean-Louis in France, who is one of the collaborators, who has done another clinical trial there, and Frank Middleton is at UC SUNY Upstate, who is a molecular biologist, director of the Genome Center, and he has agreed to do the complete genome and epigenome of the rat model if we get the funding. Thank you so much.